My name is Bruce Barker, and I work with MGS Engineering Consultants, Inc. Today I'll be giving a talk on hydrologic modeling using continuous flow modeling, mainly MGSFlood, the stormwater analysis model that we support. Just some background on myself. I work for a two-person company with my partner, Mel Schaefer. We specialize in surface water hydrology, both stormwater, and we also work in kind of the probabilistic range where we do hydrologic risk for big projects. We started back in 1997, and we're in the process of transitioning our work products over to another firm called RTI International. As of last year, they purchased all of our IT, and now we are working as consultants with them. RTI will take over sales and support of MGSFlood starting next year. And Ryan Johnson, who is probably, I think is on this call, will be the new kind of lead person with RTI that's supporting MGSFlood. So I think I've got probably a little less, like maybe 45 minutes of information here, so we can. I don't know if you want to hold questions to the end or ask them as we go along, but either way, I think we'll have some time to have some discussion at the end. So the presentation topics what I want to cover today. Some of this will be, kind of like review for many folks that are doing hydrologic modeling. I want to keep it at a high level, but I've got three main topics I want to cover. Kind of background on continuous hydrologic modeling, talk about the HSPF model algorithms that are in our model and WWHM, the regional rate runoff parameters that were developed by the USGS. I don't think a lot of people who are somewhat new to continuous modeling in Western Washington may not be super familiar with those. Then we'll give an overview of the MGSFlood model, stormwater design standards with using the flow duration standard. Then we'll talk about some of the inputs that we have in MGSFlood, our extended precip and evaporation time series, and then we'll run the model for an example application. The third topic is something new that we've been working on under a project with state DOT. DOT has a lot of projects up in areas where snow accumulation and melt can be significant, for the design of the facilities. And think about like Snoqualmie Pass, and yet they're still required to design the facilities to the ecology stormwater manual. So we basically attached a snow accumulation and melt model to MGSFlood to see what the effects of snowmelt would be on stormwater detention design, and we have kind of a couple of slides that describe that and show the effects of that. So I'm launch in here and talk about the MGSFlood. It's a general meaning you can apply it anywhere that you have rainfall and evaporation data. Continuous stormwater facility design analysis model. Kind of key features for it are it's stable, easy to use, and fast. Uses the HSPF rainfall runoff algorithms. It has the ability to specify a variety of hydraulic structures, number of control structures. Has LID analysis features as well, filter strips, bioretention, caps. And then we also have an optimization routine for automatically sizing detention and infiltration structures to meet the ecology flow duration standard. So the hydrologic processes that were simulated in MGSFlood. I've got your classic image on the left of the hydrologic cycle. We've got precip and evaporation, which are read into the program from time series that are stored in a database. And then using the hydrologic rainfall runoff algorithms from the hydrologic simulation program Fortran HSPF, we're able to compute a time series of, grab my highlighter here. Grabbing, a time series of flows for both pre-developed and post-developed conditions. I got 1 year shown here, but you can imagine this going off in both directions for many, many years. And so here's an example comparing a pre-developed and post-developed time series for a 20-year period. So the HSPF algorithm that's used in MGSFlood, it includes precip and evaporation time series based on gauge data. Simulation periods, are as long as you essentially have inputs for it. Typically 10 to maybe even 200 years, depending on the evaporation time series you use. The model is conceptual as opposed to physically based. So this little cross section that we have here shows these various layers. Those are all simulated as a series of reservoirs in the models, and that's why we're saying it's conceptual. Doesn't use necessarily physical equations in the model, but it simulates these storages as a series of reservoirs that are all interdependent. And then it computes runoff as 3 components: surface overland flow, interflow, and then base flow or groundwater flow. And then when you're using the program for sizing stormwater treatment for a typical site, the assumption is that the base flow does not contribute to runoff, and so that's off by default. So the HSPF regional parameters are based primarily on a study that was done back in the 80s by the USGS. And so the USGS developed these parameters for accommodation of soil types and land covers. They are based on 2 years of stream flow data collected continuously at a 15-minute time step for water years 1985 and 86. And so these parameters are used to estimate runoff rates and volumes for stormwater designs at ungauged sites. There have been other parameter sets that have been developed since then, based on other studies in other areas, but these are kind of the main data source, if you will, for the parameters that are in these models that we're currently using. And so this plot the map on the left shows the basins that were used for that study. There's a number that were used for developing the parameters, and then a small group down around Tacoma Federal Way that were used for validation of those parameters. And so this is an example of one of the calibrations that they came up with, and it shows observed and simulated. And overall, it does a really good job at matching, essentially matching the recorded stream flow data, for the gauges that they had. So moving along, talking about MGSFlood, giving you an overview of our program, stormwater design standards, and so forth. So when you're using these continuous models, one of the things that you're always dealing with are these flow duration curves. And so what a flow duration curve is, it's essentially the probability that a flow will be equaled or exceeded at any time. And so what they are is it's a convenient way of summarizing flow time series and evaluating changes in runoff rates and volumes with land use changes and or climate change. So the way this is done is that if you can imagine this time series on top going off in both directions for many years, is to split the recorded or the simulated flow rates up into bins, and then track the percentage of time that it resides in each of these bins. And so what you end up with is all flows, the fraction of flows are 1 down here at 0, because all flows are going to be greater than that. And then as the fraction or the percentage of time that it's occupied in each of these bins, as the flows gets higher and higher, the time gets less and less until finally you're up here at this very, very small exceedance probability that this flow would be equal or exceeded. So again, they're somewhat, these duration curves are kind of removed from the time series a little bit, so they can be somewhat non-intuitive, exactly what you're looking at, but they do provide a convenient means of kind of condensing and summarizing a lot of time series information. And we go ahead and we use these as a method for sizing stormwater controls. And so listed on the screen here are the two kind of principal design standards that we currently use in Western Washington. We use the detention standard on the left, and then another one for low impact development over on the right. And so for the detention standard, the intent of this is to minimize the amount of erosive work done on stream channels. And so this came about based on basin planning work that was done by King County and Snohomish County, back in the late 80s and 90s. They were looking at a lot of streams that had detention designed for peak flow control. And while those old standards, the event models, did a good job at controlling flow peaks, they found that a lot of the streams were being degraded severely and eroded, even though they had these event-based detention ponds in the watershed. So the theory that came out is, well, how do we correct for this? We try and come up with a method of controlling flows that don't cause stream channel or stream bed erosion. And so the thought is that you want to control all flows, the duration of flows, above the bed load movement threshold. And so that's what we're trying to get at with this detention standard, is we want to match the post-developed flow duration curve to the pre-developed level above the bed load movement threshold. The bed load movement threshold varies from stream to stream, but a value of 50% of the pre-developed 2-year rate was selected as the as kind of a generic value for the design. So that's how we came up with this. So our design goal then for detention could make sure that the developed flow duration curve essentially matches the pre-developed between half the 2-year and the 50-year is what we're trying to do. Then below half the 2-year, the duration, the post-developed curve can be above this. The LID standard came along a little bit later. And so the goal with that is to match the developed flow duration curve to the pre-developed from 8% of the 2-year up to 50% of the 2-year peak flow. And so the kicker on the LID standard, if you're trying to match this or meet this performance, is that you essentially have to have some kind of infiltration on your site in order to make this work. If you're in an area with glacial till and there's no infiltration possible, then it's pretty much difficult or impossible to meet the standard unless you have infiltration. And I think that's kind of the intent of this standard, is we're trying to distribute the flow control throughout the site and encourage and promote infiltration to the greatest extent possible. And so the output from the MGSFlood model, when you design a facility to meet the flow duration standard, the output looks something like this. And so what we're showing on here are the ecology criteria for matching the duration standard. And then the red line represents the outflow from the detention facility. And I've also highlighted the various structures that are on the detention facility that are regulating the flow. So we've got a circular orifice down at the bottom, and then a circular orifice plus a slot orifice that kicks in up at this point. And then where this line goes vertical, that's where we're going into the overflow riser crest. Right. So something that we've spent quite a bit of time on is ensuring that we have good inputs to the model to make sure that the flows that are computed by by the MGSFlood model are valid, because these are rainfall runoff models. So if you start off with poor quality precipitation, mainly the precipitation, then you're going to end up with results that are not that good. So one of the things we've done is to develop these time series, these input time series that we call the extended precipitation time series. And they're a long record. They're obtained by combining records from distant stations and then rescaling them to have the statistical characteristics of the sites of interest. So what we did was take information from 3 distant stations, SeaTac, Salem, Oregon, and Vancouver, BC, combine those records together, and then use a scaling function to rescale them to have the statistical properties that we wanted at various locations throughout Western Washington. So it results in represented precip at durations ranging from 5 minutes to annual. So why use this? It allows for the use of high quality stations with long records. It avoids the potluck of using nearby stations. Many hourly stations have short records, and they may be poor quality, or they may not be representative of the climatologic conditions that you're interested in. It provides a greater diversity and variability of storm temporal patterns. Provides for increased number of extreme events. Then it allows for interpolation of the 50-year and 100-year floods rather than extrapolation. So we've got a better handle on the rare floods that we're trying to get estimates for. So how do we do it? Instead of using a single scaling factor, we use a separate scaling function for multiple durations in the time series. So we're doing the scaling at 2 hours, 6 hours, 24, all the way up to annual. And so instead of using a single scaling factor, we're using a function that the scaling factor here, that's a function of the mean and the variance of the target station and the mean and variance of the source data that we plug into it. And so when we do this, we're able to maintain, essentially the characteristics, the statistical characteristics of the rainfall in the target site, and use this longer record that we have. This is complicated because we're doing these scalings at all these different durations. And so a lot of these durations are all nested within each other. So it gets pretty complicated in terms of doing scaling and maintaining the statistics at each duration. So it's a iterative process that we go through to get these to work out properly. And as it says down here, it produces the desired means and variances at our target site. And so these are just kind of proof graphics that we have, where if we take the annual max from our extended time series, which are the blue squares, plotted up on the regional precip frequency relationship, then we come out with a good match for all the durations that we did the scaling at. So I've just shown 3 of them, shows that for a short duration of 2 hours, 24 hours, and at 365 days. And you can also notice that the shape of these regional curves changes with duration too. So that's part of the trying to come up with the maintaining that variance that I was talking about in that scaling function before. So the extended time series in MGSFlood, they're up to 208 years long now, stored on a 5-minute time step. Originally, they were 158 years, but we've updated a number of them using additional data that's been available now since we originally did it. So now they're up to 208 years long, stored at a 5-minute time step. Again, this provides better estimates for a range of storm durations, more robust stormwater facility designs, and again, this whole issue that we're getting better estimates for the rare floods. So, how does this work? In the model, I can run a quick design for a project. This is one we use in our training. It's 1.34 acre road widening project where we're designing detention for it, pre-developed condition of forest, developed condition of impervious. So if I bring up the MGS model, so I've got everything already entered. And then over here, I'm going to run this at a 15-minute time step. I've got 208 years at 15 minutes. So we're going to do the analysis for. So I'll just click route. I'm going to tell it yes. I'm going to have it automatically size the facility. And so now it's cranking through and it's computing the runoff for the 208 years. And then now that the runoff for the pre and post-developed conditions are complete, it's going through its optimization routine and it's doing the automatic sizing. It's trying multiple outlet configurations and sizes to try and come up with a facility that meets the ecology duration standard. So it's complete. If I click OK, then it jumps back and it shows us the duration performance. So even though we're looking at a lot of information, I think we're cranking through like 5 million data points on the time series. The model cranks through it pretty quickly because of some of the algorithms that we developed to process data a lot faster. So it runs very quickly. Again, if I want to redo this and run this at a 5-minute time step, I can do that. Click route. Okay. And so even at 5 minutes, there's really not an appreciable difference in terms of the computational speed. We'll see a difference in terms of the results on this. So now we don't meet the design standard because I ran at 5 minutes because I'm getting higher peaks in my post-developed condition. But that's just an example of kind of how the program works. And then our output is put up here in the project report. So. All right. So that's a quick overview of the MGSFlood software. And so my last topic is kind of the new stuff we've been working on, which is inclusion of snow accumulation and melt and the effects of that for stormwater detention design. So this is that picture up there is a snowtail site. I think that's up near Packwood off of Skate Creek Road, I believe. But these are some of the stations, some of the snow collection sites that you can get data online to help with your model setup and calibration. So our routine that we have at MGSFlood with snowmelt, so we implemented routines to address snowmelt for projects in higher elevations. This was something that DOT is interested in. Currently, the ecology doesn't recommend continuous models for watersheds with mean elevations above about 1,500 feet due to snowmelt influence. So what we did was we wanted to implement an energy budget snowmelt algorithm into MGSFlood. So the routine that we selected was one that we have a lot of experience with, and does a really good job at mimicking the snow processes in the mountains in Washington and actually throughout the West. It's based on the University of British Columbia, the UBC snowmelt model, and it's well suited for our mountainous regions around here and also in California. It's a continuous hydrologic model developed by Quick and Mikovic at the University of British Columbia. It works really well where sparse meteorological data is available, which is almost anytime you're dealing with mountainous conditions. The model does a really good job at replicating observed snowpack and melt with relatively few input time series. The snowpack simulation routines were adopted for use in SCFM, which is our stochastic flood model, and MGSFlood. And so these graphs down below are some example snowwater equivalent, seasonal snowwater equivalent that were computed using the UBC model for a couple of projects we worked on. This is Tuolumne Meadows, which is down by Yosemite in California. Tipton, which is a project we had down in Oregon. We've also applied it to a number of projects in Washington State, and we came up with a set of kind of regional parameters that we use for a lot of our projects. And so that regional is probably the wrong word. It's probably they're more like a set of parameters that our default ones that we tend to use when we first start doing our watershed analyses. So these parameters reside as a text file in the project folder. Default parameters are developed from calibrations at several local watersheds, the Tolt, the Skokomish, and then multiple watersheds in California. So the user, in theory, could just take these and run with them, essentially, similar to what we're doing with the USGS regional parameters. But because this file with the parameters exists in the project directory, if you did want to do some adjustments to, say, the lapse rates or some of the other parameters in the file, you have the opportunity to do that. So I have an application of it to a hypothetical site up at Snoqualmie Pass. We have, here's our project site. Elevation is 3,020 feet. Locating 15-minute precip and temperature is really lacking up in the mountains. So we actually, I tried to use data that was closer to our project site, but it's just very poor quality up there. So that will be something that we'll have to work on going forward, is if this is going to be implemented, kind of more region wide, then we'll have to come up with better time series inputs to make this run. One thing I guess I didn't mention is the inputs we need to make this work, in addition to precipitation, is hourly or 15-minute temperature. Those are the only parameters that are used. Other snowmelt models, such as HSPF, require a lot, many more time series. You need dew point, solar radiation. The dew points and the other parameters that are needed by the snowmelt model and the UBC are all they're essentially estimated by algorithms internal to the program. So in terms of time series needed to operate it, it's a lot less than with other programs. So the inputs that we use for my test case, I grabbed 15-minute Darrington precipitation, which had 25-year 24-hour precip of 5.43 inches, temperature from Stampede Pass, elevation of 3,900 feet. And so we translated the Darrington precip to the Snoqualmie site using the ratio of the 25-year 24-hour, which in this case was 1.45 times the precip at Darrington. Temperature was from Stampede Pass. It was lapsed to the elevation of interest using the algorithms in the UBC model. And so our simulation length was 63 years at a 15-minute time step. And so then in MGSFlood, we've got this new checkbox that you click on here that tells it, yeah, I want to do snow melt. And so that tells the program will then go and look for the temperature and time series that it needs to do the snow accumulation. And then the UBC snow routine was compiled as a 32-bit DLL and then connected to the program. So some of the results. Oops. There it goes. So here's the output for the Snoqualmie Pass site. What this graph in the top shows is we're showing snowpack is the blue line, snow water equivalent for a number of years, and then the kind of orangey line up here is temperature. So again, the snowpack in blue, it generally peaks in April, typically fully melts out by middle of June. And so then if we take a look and see what's going on down below with respect to moisture input to the soil, the light blue is precipitation, the dark blue is rain plus snowmelt. So what's happening on this is, when we don't include snowmelt, then we get these light blue values represent the moisture inputs to the soil. When we include snowmelt, a lot of these storms that contribute to runoff in the wintertime fall as snow and are released in the spring at lower rates when the snow melts. So in effect, we're getting kind of a de facto detention with with this moisture getting tied up in the snowpack. So overall, the moisture input rates are reduced. You can look at this spike here, this storm here, which if you didn't include snow, all that moisture would come and fall and produce a pretty good sized runoff event. And when you do include snowpack, then now all that fell as snow. So this is just zooming in, looking at this a little closer. Again, we've got the same thing. We've got these light blue representing the precip. So these are winter periods where precip falls as snow, does not contribute to runoff immediately. Moisture inputs are less in wintertime, reduces the winter runoff rates. And then, like I said before, the spring snowmelt, you can see where this is coming off in the spring. It acts as detention. In terms of our flood frequency response, this is a comparison for the with and without snowpack for an impervious site. So you see we've got a little bit of a reduction in the peak flows that are coming off during kind of these more common events. And that reduction is due to some of these storms falling as snow and not contributing to the peak flow runoff. So what's going on with these two storms up here is that those were actually occurred in the summertime due to convective events, and so they were not affected by snow either way. So we ended up with the same value for those two events. So similar flood frequency plot, but this time for the forest condition. So again, we're seeing with the snow melt, with the snow accumulation included, slightly lower peak flows coming off during the winter time up until we get to this point. then we see, again, it comes again. I'm sorry. We see slightly lower, and then when we get up to these two events up in the summertime, now we're seeing higher runoff rates. And again, these are the two same summer storms that we looked at before with the impervious runoff, but now we're generating higher peak flows for the forested site. And the reason for that is that we've got snowmelt occurring in the summertime, causing wetter soil conditions. And so our pre-developed runoff rates for these higher events are higher when we include snow accumulation and melt. So what happens with our detention designs? It's not as much as you would have thought, or I would have thought, in terms of volume. So this plot on the left is a detention facility that was sized using the same inputs, but we didn't include the snow accumulation and melt. We came up with a detention volume for 2 acre. This is 2 acre forest to impervious. We came up with a detention volume of about 1.29 acre feet. Same site, everything the same, except with the snow accumulation and melt on. We came up with 1.299 acre feet. And the reason for that primarily is because we've got slightly lower pre-developed runoff rates estimated down at the areas where we're sizing the outlets for, mainly at the 2 year and half to 2 year rates. So that's kind of the takeaway, I guess, on this. Yeah, the volumes are a little bit different, and yeah, you have slightly different outlet structures, but overall it's really not that as different as you might originally think. So this is just a summary slide, summarizes everything that we did, but kind of, again, the key takeaways: the pre-developed peak flow rates are lower for recurrence intervals, more common than the 10-year recurrence interval. The same for recurrence intervals, rarer than the 10-year. So inclusion of snowmelt resulted in slightly larger detention facilities due to the lower pre-developed conditions. Winter runoff rates where many of the storms fell as snow. So where are we going to go with this? DOT is still kind of mulling it over. Do they want to kind of continue on with this and develop higher quality time series so that they can use this on other projects? It's still being decided at this point. Or the alternative is, kind of looking at these results here. Things aren't that different by not including it. So remember, this is also a site that's at 3,000 feet. There are, other sites, obviously there's a range as you go, lower in elevation, there's going to be a mixture as we kind of transfer from, a winter snow dominated system to kind of a mixture of rain and snow as you get down lower in elevation. So, trying this out on other sites would be, I think, informative as well before they make their choice. So. All right. Look at that. I got done in 45 minutes.
Perfect, thank you.
All
So
right.
it looks like we do have one question in the chat from Scott. Is MGSFlood significantly faster than WWHM? Does this program take advantage of multiple core processors?
Right now it doesn't take advantage of multiple core processors. The speed that we were able to achieve with it has to do with the rewriting the HSPF algorithm so that it runs using a variable time step so that the program shifts to longer time steps when it's dry out. So we've recently put this on here. So we recently rewrote the interface and to using a modern Net Studio programming framework. So the next version, which will be out in early next year, it's actually in testing right now. It could use multiple cores. It's 64-bit, and it's got better graphics. And then in terms of installation and maintenance, it's a lot easier. And if anybody would like to try out the 64-bit version, send me an email and I'll send you I'll let you try it out for free. We're trying to get users to play with it and beat it up and test it a little bit. So if you're interested, shoot me an email and we'll get that out to you.
Perfect. And then there's another question from Caroline. In the new model version 4.68, will facilities get bigger due to precipitation time series updates?
Yeah, that's another good point. So the original precip, extended precip in the model was 158 years in length. That was based on data through 1999. So I'll go back to this guy right here. So we had data. These dates on here are kind of arbitrary, but the first one, 1940 to 1999, was kind of the parent time series that we use from SeaTac, Salem, and Vancouver. So we've got 24 years of additional data available. Under a project for Pierce County, we updated the time series used with that additional information. And there are a number, the first part of the 2000s were pretty active. There were a number of very unusual storms that happened. My partner, Mel Schaefer, redid the regional precip frequency statistics, and those increased slightly over the original ones that we used when we sized these. So the new updated time series are 208 years in length, and they produce higher runoff rates than the original time series did. So the short answer is yes. If you use these updated extended time series, you'll find that your facilities will tend to be, they can be larger. If they're infiltration facilities, they'll be larger. If they're detention, they may actually be smaller. And the reason is that detention facilities, the release rates are determined by the pre-developed runoff rates. With the higher precip or the higher storm values, you get higher pre-developed runoff rates, higher release rates, and you may end up with smaller volumes, at least for detention. For infiltration, water quality treatment, it'll be larger.
Okay, and then there's a question from Paul in the chat. Is there a developer API we can use to automate the model?
Oh, there isn't right now. That's a good question. I hadn't thought about that actually. Paul, if you want to send me an email and let me know what you're thinking on that, we'll see if we, I'll give it some thought.
And then there's another question. Does variable time step adaptation still perform comparably when groundwater response is factored in?
Yeah, it doesn't. It's computing the groundwater response regardless. It's just not including it in the calculation. So when you turn it on, all it does is just adds that flow into the calculation. So it doesn't affect the runtimes at all.
And then another question is, does WWHM and MGSFlood basically generate the same BMP size to meet the requirements and provide the same results? And are there any key differences you would like to share?
They are using the same algorithms, and so if we use the same inputs, then they produce essentially the same designs. So I mean the only probably if I'd say probably the biggest difference is mainly speed because of that variable time stepping algorithm. So if you're in Seattle, for example, they require 5-minute time steps and 5-minute precipitation for a lot of their designs, and those can take a little longer with WWHM. But again, the computers are so fast now. Um, Back when we first started doing these, you would do a simulation, walk away and go get a cup of coffee and then come back. But now it's so fast, it's not even funny. So
Sounds good. And we have another question. Appreciated the history behind regional runoff parameters. With the ease of continuous monitoring, has there been a fresh look at baseline calibration work to update regional runoff parameters?
yeah, not that I'm aware of, and I don't know if there's anybody from. I thought I said was Doug Byerline on there, but somebody else from maybe Clear Creek if they're on, if they know of anything that's gone on. There's a lot of these parameters do a good job. We've used them in basin planning studies where you apply them as a starting point, and then when you have gauge data, there's still some minor tweaks that you would make to maybe calibrate the model. But overall, they do a pretty darn good job, I think, at estimating runoff. But one thing that we don't typically do is quantify uncertainty with our designs, and that's something that could be looked into. I think is because we're applying these parameters to ungaged sites. What are the uncertainty bounds? Could we do an analysis with these and come up with the best estimate with 90% uncertainty bounds? But that would be something that would be interesting to try. And I think it could be done, especially with the speed of computers. You would end up doing designs instead of once. You would vary the parameters and the preset, do many simulations, many designs, and then come up with bounds on your answer. So I think that's just something to keep in mind. Is there's uncertainty, there's a lot of uncertainty for a number of different factors that nobody is really addressing with any of this stuff. So
And then another question is, it seems that actual snow melt on impervious washdot surfaces such as roadways is affected by traffic, sanding, and salting of the roadways. Is this effect recognized in the algorithms?
it's not at this point. It's not to say you couldn't, if we had some information on even if it was just conceptual information on how they believe or how they've observed the snow melt to occur, we could probably adjust some of the parameters in the model. But essentially it's not taking that into account at all. So that's a really good point too. Yeah, because there is plowing and plowing occurring too. So that's a good point.
And then looks like we have one last question in the chat. Are the updated time series taking climate change into account? Are we able to upload projected precipitation data for specific locations in Western Washington into the MGSFlood model instead of using the updated time series data you were discussing earlier in the presentation?
Yeah, no, I mean the answer is we do not have. Let's see here. Let me think about this. You can load climate adjusted time series into the model. There's a user defined database the program includes. So if you had that and you wanted to run it, you could. We have set up the MGS flood model for climate adjusted time series for the city of Seattle. And there are time series for Seattle that I think it's 2050, 2075, and 2100 time series estimates for those. So yeah, but the short answer is we do not have them for all locations. It's something that a lot of jurisdictions are looking into. We work our partner firm RTI has a meteorological group that does this kind of work, and we've worked on it on other projects where they will actually take global results from global climate models, downscale it, come up with scaling factors for the time series, and then give us climate adjusted time series for our models. And we've done that in a number of locations. So that's something that could be done, but it doesn't exist for all areas of Western Washington that I'm aware of.